All right. So we are going to continue off with lecture series number 7, I believe. I do apologize that the screencast actually took a while to produce. It's just that I've been busy these last couple of days. But if I can just get to the directory with the slides here, it'll make life a lot easier, I guess. All right. All right. There we go. So like I said, we are transitioning into lecture series number 7, which is loosely tagged as being model implementation using machine learning. It's essentially just meant to be a sort of introduction to the traditional machine learning techniques. And most of this would take the shape and form of just a brief walkthrough of things that we probably are already aware of. At least I hope the vast majority of us will already be aware of these things. If not, I suppose the the walkthrough will try and sort of like remind us of the machine learning aspect of most of these tools that we tend to use. And then I also thought it would be interesting as we walk through the different examples of the traditional machine learning techniques. I thought it would be interesting if we were to latch on to some of the seminar talks that were given by invited speakers as part of the seminar series. All right, so as always, I guess the lecture series is going to be split up into 2 parts. I should mention up front here that the Jupyter Notebook is essentially just a short walkthrough because most of it involves us just going through a few examples of how you get to create a training set and a test set essentially. And we just focus on the holdout method and so-called K-forward cross-validation. All right. I should mention up front here that most of what we're going to do is going to focus on, or a lot of emphasis is actually going to be on model evaluation, right? Just because we feel it's the most important aspect of this discussion, right? So we're going to spend a bit of time doing this. The sort of things that we discuss as part of brief introduction, model introduction, machine learning and machine learning techniques are for the most part things that are pretty much intuitive, but from past experience what we've noticed is that most students tend to misrepresent or struggle with the evaluation aspect of these models that we tend to implement. All right, so on with it, I suppose. I can just take it to full screen view. And just to remind those of us that have forgotten that we're using the CRISP DM as a guide. So we've essentially been walking through some of these steps here, right? And I guess one of the reasons why I thought I would include it in this lecture series is because if you remember, Nock's presentation last week was loosely guided by a completely different data mining model, right? So it was grounded in what's called the KDD process. These things are more or less the same. There's just a few subtle differences. If you notice the KDD process, for instance, if you remember the visual representation of the KDD process that Knox kind of like shared with us, and maybe now would be a good time for me to just go here. If you remember, the aspect of deployment was sort of like hidden within that model itself, right? So if I can just get to the talks here. Ooh, invited talks. Right. And I'd like to think that people probably already have an idea of what it is I'm talking about, seeing as one of the one of the readings associated with lecture series number 2 was actually a meta-analysis of the different data mining models that are different data mining models that are typically used. So if I can get there. All right, so this is what I'm referring to here, KDD process, right? Like I said, if you are to compare this with a CRISP-DM model, some of the phases are pretty much the same, although different names are used here. One would argue that the CRISP-DM model tends to place an emphasis on preliminary activities that one would need to undertake before you actually initiate the data mining process. And specifically by initiating the data mining process, I'm referring to, I guess, a part that would involve you collecting the data. So if you notice here, the initiation of the data mining process when it comes to the KDD process starts with data selection, right? But for the CRISP-DM model, it starts with business understanding, right? Another difference that you immediately notice here is the fact that there's no explicit tag associated with deployment. Everything ends on evaluation. If you look at the CRISP-DM model, on the other hand, you have a deployment phase here that is explicitly stated. Now, one would argue that if you really thoroughly go through the KDD process and what these different phases mean, they probably sneak in aspects associated with deployment somewhere. So you can immediately see here that evaluation, right? Evaluation is loosely associated with patterns, and whenever you're talking about patterns, that's really linked to deployment, right? You can only ascertain patterns or figure out what sort of patterns exist once you evaluate your model, you implement it until you evaluate it. All right. So again, our discussion for this lecture series is going to include, it's actually model implementation and evaluation, right? So it's not just model implementation, but and evaluation. So we discuss these things together in this lecture series. And then in the upcoming lecture series, we also focus on the two aspects, because we really look at we discuss in detail the individual traditional models, specifically linear regression, machine learning techniques rather, linear regression, classification, and clustering, right? But as we discuss in those different techniques, what you notice is that aspects of model implementation and evaluation will come in. All right. And if you remember, so what this process involves, right? The model implementation process involves is defining. This is where you get to define the different components that are associated with the model. So it will be everything from the input features that you feed into this model that you're implementing, the specifics of what sort of estimators you're going to experiment with, right? And then there's some aspect of evaluation still associated with model implementation, and specifically as you are assessing or trying to figure out which estimator you're going to incorporate into the model. This is when you get to do a bit of preliminary evaluation, essentially, right? So as an example here, we're saying you'd probably end up, if you're solving a classification problem, what you end up doing is trying to evaluate the different classification estimators or algorithms. Again, right. So brief introduction to machine learning here. The goal really, right? The goal of machine learning is to try and make sense out of large volumes of data, right? Fundamentally, that's why we use these machine learning techniques, irrespective of whether it's linear regression, whether it's classification, whether it's clustering, or whether we're taking advantage of so-called deep learning techniques. What we're fundamentally interested in doing is to try and see if we can identify patterns and associations, right? And those patterns and associations would typically take different shapes and forms. So in the case of techniques such as linear regression and classification, one of the things you'd be interested in is to try and predict an outcome. So for linear regression, for instance, you might be wanting to predict perhaps a numeric value into the future by making use of historical data, right? For certain problems, though, it might not necessarily be, you might not be in a position to know exactly what it is you're looking for, in which case you just use techniques that will reveal some sort of pattern that exists in the data that you're working with. And this is where clustering comes in, right? So with clustering, you're not really, it's not always the case that you're certain what it is you're looking for, but in terms of specifics, what you'd be interested in doing is to try and see if you can identify patterns, and you use the patterns to try and make sense out of the data, essentially. In certain instances, you tend to use machine learning techniques to try and identify what sort of cause and effect relationship exists between your independent and dependent variables, right? Your independent variables being your x's, your input features, and your dependent variables being the y's. And really, the way that you go about doing that is just to make use of so-called associations, really, right? So you'd perhaps be able to figure out to say, oh, there's a causal, the demographic details of the students, and specifically maybe the age, has a causal effect on the learning outcomes. And I'm reaching here. I don't know that. I don't know if that would be the case, but maybe in certain instances it might be the case, right? Right. So, with that being said, what you immediately notice is that if you think about it, machine learning has a number of aspects associated with it. In mathematical terms, you can actually view whatever it is you're working towards as a mathematical function. A mathematical function that always takes in input data, right, which we can actually assume or view as being the x, and the x influences the output, which is of course the function of x, which would be the y, right? So in almost all instances, whenever you're working on a machine learning problem, what you're doing is you'd view the problem you're solving as being a mathematical function where you are interested in finding out a y, right, relative to the input data that you're working with. And this raises really interesting things here, right? The most important one being that in order for you to solve a machine learning problem, you need an X, right? You need data, right? Data happens to be the key ingredient to any machine learning technique, right? And so based on what we discussed, what you notice is that this function could be viewed as being a function that is a function which is meant to be used to predict an outcome, right, based on the structure or the features associated with the data, or the function could also be aimed at trying to reveal patterns that exist in your data. Okay. And in as much as we're saying the X is the data, but really what we are trying to say is it's the attributes associated with the data. And remember, when we are talking about attributes here, your data could be associated with a broad spectrum of attributes. If you're working with text, the attributes you'd be looking at could be perhaps the term frequencies associated with the text itself, right? It could be your term frequency inverse document frequency, your TF-IDF, right? In certain instances, I think I just lost power here. That's fine. In certain instances, it could be something much more complex. What we'll soon see in some of the examples we're going to look at is that in certain instances, it becomes imperative that you try and combine the effect of all the different attributes, right? So you could think of the X as being composed of, let's say, the age demographic details of the students could be associated with the students' course minors, for instance. And you combine all of those to come up with a merged version of X. And really combining different features, right, or different data attributes is something that you tend to do explicitly or implicitly as you're evaluating these models, right? Because there are certain instances when you might, not certain actually, it's almost always important for you to check if the resulting output is better when you use the attributes in isolation, or if it is better if you combine the different attributes. So I don't know if I'm making sense here. In the event that you're working with user demographics, for instance, right? User demographics, let's just assume we're working with two attributes, user demographics and course majors, right? And we want to figure out what sort of effect these two data attributes have on the, let's say, the performance of the student in the exam. You could view this problem as being in two parts, right? It's composed of two separate parts where you'd start off by assessing the demographic, right, of the students to try and see what sort of effect it has on the outcome, prediction of the outcome. And then you'd later on look at the course majors, or the course minors rather, right, and try and see the effect that it has on the function. But also, what you could do is, or what you should do is, you look at the combined effect of these two variables, right? So key thing here is that the X here, in as much as we're saying the X is the data, but we're saying that the data attributes are what we are interested in. Even more interesting is things like maybe a combination of different sort of data attributes that you'd be working with. All right, I hope I have enough power to finish through this screencast, and I'm lecture slide number 7 of 83. Wow. Okay, so again, input is generally attributes associated with the data set. And the reason why this reliable data is in bold here is we are making the assumption that at the stage when you're implementing the model, you'd have already cleaned up your data, you'd have already pre-processed the data, right? So you'd have already made a decision, an informed decision as to how you'd handle iffy issues like missing data attributes, for instance. Do you exclude observations, data observations that have certain attributes that are missing? Do you come up with a derived value for the missing attributes, right? So bottom line is the assumption that the data we're referring to here has to be the reliable data that has already been pre-processed. And you notice by looking at the CRISP-DM model here is that would have already undergone all these different phases here, right? So that by the time we get to the modeling stage, the data that we're working with is complete and comprehensive. All right. We know that by the time we get into this stage, we would have already transformed the data, right? And transformation is important. We've already had this discussion, but it's always important to wrap this in. Transformation is extremely important because the estimators, for the most part, will expect the data to be in a numeric form, right? So if you're working with a data set that has attributes that are, let's say, ordinal in nature or categorical in nature, right? What you want to do is you want to make sure that you use appropriate techniques to transform them in a numeric form that the estimator is expecting. And we know how to do this by now, right? It's techniques such as one-hot encoding, for instance, which is pretty straightforward here. So again, the data representation is dependent on the problem that one is wanting to solve here, right? So it might be the case that maybe you might be interested in predicting whether a student will fail or pass, in which case you notice that the prediction here is it's a binary, right? Yes or no. Pass or fail could be yes or no. Or you could be interested in predicting a numeric value. That's linear regression or regression, really. This is why the JCTR basic needs basket is here, by the way. I'm not sure if just pause here. I thought I'd included this to a certain extent. No. I guess now would be a good time to just because this is probably going to come up or pop up every now and then. Now would be a good time to just explicitly state that if you look at this function, right, your x is the independent variable and your y is a dependent variable because you're measuring the y. Whenever you're working through a machine learning problem, your dependent variable is the y. This is what you would be measuring or interested in measuring, and then the x would be independent variables, right? So independent variable is the input, and then the dependent variable is the outcome or output in this case. All right. Again, just remember that this is a mathematical function that we're working towards. All right. So we're just going to. I'm trying to see if maybe I should pause here. Yeah, I suppose I will pause. Sorry, this is a bit haphazard. I will pause and then I'll break this up into small little pieces, and then we'll continue off with some examples of machine learning techniques.